Welcome to my presentation on non-parametric models for long-term autonomy. You are a bat. It's nighttime. You're hungry. You just woke up. You want to go out and eat lots of insects. Step number one. Do we have a question there? Can you hear us, Alice?
We got a thumbs up.
Assume we're good. Okay, good. You're a bat. And step number one is you have to be able to get out of this cave without hurting yourself. You need to know where the stalactites and the stalagmites are. So you use echolocation. You make a sound with your mouth, it bounces off the stalactites and stalagmites, and you hear how long it takes to get back to you. And you use this to figure out its location. This way, you're able to fly around without hitting anything. And as you're flying through the cave, you make a mental map. You remember your trajectory, and you remember it well enough that if you get back to some point of it later, you'll remember where you are. And doing this, later on, after you've eaten your whole night through, you'll be able to fly back to your favorite roost and sleep where you like to sleep. Finally, you exit the cave. You're in the forest. Now you have to make a plan. You want to eat as many insects as you can, but there's only so much time. Do you stay close by to the cave to not waste time flying, just start eating there? Or do you spend more time and fly out to the pond where there's even more insects? Or maybe you explore, fly out by that barn you haven't been to yet? In this research here, in this presentation, I want you to imagine a robot that can have capabilities similar to that bat we've just been talking about. A robot that can locate objects and itself with the same precision. A robot that can map difficult environments to be able to navigate through them effectively. A robot that can plan its time and resources as effectively to accomplish its own goals as the bat to accomplish its. Because bats are very, very good at this. Bats eat thousands of insects a night. They're in natural environments that are constantly changing. They have to adapt. And they can live for up to 30 years. Imagine a robot that could work for 30 years effectively without us constantly prodding and fixing and giving it updates. So this presentation, our goal is long-term autonomy. So what do we need for that? So again, these three aspects here that we have are localization, estimating the position of the robot and of other things in the environment. Mapping, being able to remember the path that you've taken through some environment and be able to recognize when you've returned to that path or some part of it. And planning, being able to take the optimal action in order to accomplish a goal. And for all of these, the robot has limitations. It does not have a perfect knowledge of the world. It only has its own limited observations. It likely does not have a supercomputer to power it. It likely has a much smaller computer and limited abilities to perform computations. So to be effective in long-term autonomy, we need to be effective at using our limited resources to accomplish these different things. Now, in accomplishing all this, the focus on this presentation is on non-parametric models. So what do we mean by that? Well, imagine that I have a favorite restaurant, and I want you to go try it out. The problem is I don't remember exactly where it is. I have a more fuzzy memory of it. And so I could give you a map of where it likely is, and that map might look like this, for example. This is a very simple map. We have X and Y. You can imagine this overlaid on Google Maps. And we have the color here, telling us how likely it is. So most likely it's in the middle. Maybe it's a bit farther out. This is a simple parametric model. But maybe the truth looks a little bit more like this. My memory is really very scattered, really very fragmented. And if I could tell you everything I remember, it would look like this. Well, you would start probably by looking for the restaurant in the middle, the same either way. But if you don't find it in the middle, what you end up doing later will change very much depending on whether I give you the simplified model on the left or the more complex one on the right. And the point I want to get across is that if it isn't close to the middle, you likely won't find it if I give you the map on the left. It'll take longer to find it on the right, but you probably will find it much more quickly if I give you the whole truth. And so the emphasis here is, even if the whole truth is messy, let's give you the whole truth. It'll enable more effective planning in the long term. So in this presentation, first, we have a chapter on the location aspect. Where is the robot? Where are other things? Then we'll move on to a chapter on mapping, remembering the path the robot has gone on and coming back to recognizing where it's been before. And then on planning. How do we be effective at accomplishing a given goal? And finally, if we have time, we'll also take a look at the appendix of our thesis, where we did additional work on planning. It was not as successful as the work in Chapter 3, but there's a lot of interesting work and research and thoughts that went into it. Chapter 1, Non-parametric error modeling for ultra-wideband localization networks. I want you to think here again of the bat using echolocation and hearing how long it takes for the signal in order to figure out where these obstacles, stalactites and stalagmites are. More specifically here, we have a picture of our old lab, and our 7 circles. They represent radios that we placed in different locations. And these radios to the robot are a little bit like the stalactites and stalagmites, because when the robot sends out a signal to one of these radios, the radio will just send it right back. And the robot can listen for how long that takes and know, therefore, how far away that radio was. With enough of these measurements, the robot can figure out where all of the radios are, and then it can also figure out where it is in relation to those and navigate by them over time. Now, I have this map here also marked as easy, right? And it's marked as easy because the floor here, it's all very, very clear. There is nothing in between any of these radios to get in the way to make it harder. Well, we also tried it the harder way. Here we have lots of boxes. Some of these boxes have heavy metal pieces in them. There are also robots in between some of these radios, a lot more heavy metal. And all of this makes the problem much more difficult. And the reason it makes it more difficult is because when the robot sends a signal to one of these radios, maybe instead of going right to it and then right back, maybe instead it bounces off a box, bounces off the ceiling, gets to the radio, bounces on several more things, and then gets back to the robot. Well, all that bouncing means the signal will take more time to get to the robot. More time, and the robot will think it is farther away than it really is. And so this makes it much more difficult for the robot to locate those radios. And this means the robot may measure many different distances to any one of these radios. And it makes it a much more cloudy picture to figure out. Now, we're going to be solving this as an optimization problem, and there's some extra difficulties to that as well. One is a nonlinear bias that is dependent on the range. Another is that each radio has an antenna delay that is subtly different, so we can't exactly treat them all the same. And there's also a geometric problem, flip and discontinuous flex ambiguities that lead to local minima in the optimization. Let me give an example of that. Say the robot is at point A, and it already knows where point B is. Now the robot has managed to make measurements of the distance from point A to C and from point B to C. But is point C on the left-hand side or is it on the right-hand side? It could be flipped either way. The measurements agree just as well. The contributions of this chapter include explicit coupled modeling of radio antenna delays and locations in a maximum a posteriori formulation, a framework for incorporating non-parametric kernel density estimate error models, robust triangulation and multiple initializations, and open access source code and data for comparisons with our method if anyone else wants to make fair comparison. And in the end, we end up with very good results. In this figure here, the y-axis is error in meters. So the lower the error, the better. And on the x-axis, we have the 4 different data sets that we collected. Number 1 is the easy picture I showed you before. Number 2, 3, and 4 each have more boxes and more clutter placed than the last one. And that's why in general you see that the error goes up to the right. The important thing now, though, is noticing that in each case, the best error and the most consistent error comes from some version of our method versus the other ones here. The alternatives that you could do for this kind of problem, the simplest thing is if you could identify radios that have clutter between them and you just discard that data. Assuming you have enough radios without any clutter in between them, then you might still have enough to solve your problem. There are other optimization approaches that we could take as well. One is called simulating annealing, where essentially, as an optimization, all of the locations are shaken around and perturbed until they settle down into a good positions. There's also semi-definite programming, which is where you solve a suboptimal problem, that is a relaxed version. And then there's also multidimensional scaling, where we approximate a gradient descent and do an approximate form of optimization. Several of these methods, though, I'll note, involve approximations that we're trying to avoid with our non-parametric approach. So to solve it as an optimization, we have to do some mathematical modeling. The thing that we start with, the actual measurement we take between two radios, is the time it takes to leave one chip and get to another chip. But in order to make a relationship, we need to know how much time the radio waves actually spend in the air, not just from chip to chip. So we have to subtract out this antenna delay to get the time of flight of the signals in the air. Once we have it in the air, we can multiply by the speed of light to get distance. But then we also have to subtract out the range bias, which again is nonlinear. And then we also, for comparing this, have our own distance that we're predicting from our model with where we currently think everything is. We solve it as a joint optimization problem with the positions x in the antenna delays, and it has this form of graphical model. Now I want to talk a little bit about the kind of data that we actually see, right? So here we have two radios set at fixed positions apart from each other without any clutter between them, keeping it really nice and clean. And we took several thousand measurements in a row between these, and we made a histogram. We made this histogram here. On the bottom x-axis, we have the time of propagation in microseconds. And I'd like to point out that 0.001 microseconds is 30 centimeters as far as the speed of light is concerned. On the y-axis, we have counts, because it's a histogram, how often we get these measurements. And this forms a nice bell curve. So if all the data are always like this, we could have nice parametric models, everything would be very easy, and it'd be wonderful. But what happens when we start putting some clutter in between? Well, we start getting something like this, and with even more clutter, we start getting something like this. In the latter part here, the arrow on the bottom corresponds to multiple meters, and it becomes very unclear what we would say if we tried to represent this with the bell curve with a Gaussian. And so we say, how about we don't? Let's leave this data to have the shape that it appears to have here as much as we can. But in order to use it for optimization, we still have to do something. So we smooth it out. We use a kernel density estimate to smooth it out into a continuous function, and we get these versions. And they, importantly, very much follow the original shape. They still contain essentially all the original information. They're just a bit smoother. From these, we can take gradients. And with gradients, we can perform an optimization, such as with Gauss-Newton. The second thing we need to do is have some help with the problem of all the geometric ambiguities, since we have the flip ambiguities and other things that lead to multiple local minima. And so what we do is we start with multiple initializations, multiple starting points. We make sure that each of these starting points is geometrically robust. And we try these out and see what turns out best, what ends up fitting the data best. Again, this is a reminder. This is what the radios look like in their positions. And then with 3 initializations, here are some examples that we got. The first one doesn't seem to fit at all well. The second and third both seem to fit pretty well. And if we look at the cost here, that number is lowest for the third one, meaning that the data appeared to fit best for that. And so 3 is what our method actually returns as its solution for where everything is. And again, with our results, compared to these alternatives, we got the lowest error and the most consistent error for each data set. Interestingly enough, we even got the lowest error in the easy data set, where we thought everything would look Gaussian. So apparently sometimes there, the question is a little bit more complicated as well. Chapter 2, the masked mapper, masked metric mapping. So here again, the problem is the bat being able to remember its path through the cave and being able to recognize when it gets back to the path, so it can follow it in reverse. The problem we're looking at a bit more specifically is that robots can get disoriented. That is, over time, if they're uncertain in their direction, they will gradually get lost, gradually farther and farther off, because a small error in the direction you're pointing gradually accumulates the farther you go. The key to solving this problem is generally considered being able to recognize when you get back to it. That is what we call in robotics a loop closure, because the robot will have traveled in some form of loop in order to get back to a place it recognizes before. And so the ability to recognize places is the key to making a good map here. Here's an example of a robot getting disoriented over time. At the very end of this, the robot thinks it's way off on the top right of this, but the truth of the matter is actually it came back to its starting point. It just got very disoriented. Now, another problem with this is if you need to recognize a place you've been to before, you need to make sure you don't accidentally recognize a place when you really are not back there. The problem of thinking you're at a place when you're not is called perceptual aliasing. And in a building environment, this generally happens in hallways. Hallways all seem to kind of look the same. So like robot position 1, robot position 2, different hallways, but they look the same to the robot. Especially where a robot has LiDAR and is only seeing distances as opposed to other details like color or texture that might help. The contributions in this chapter include a flexible approach to masking, meaning deciding when locations should even count as recognizable in a high-performance mapping system to lower computational cost and reduce perceptual aliasing, and 2 effective masking functions based on detecting openings and intersections. We also give a demonstration of this on a 2.5-kilometer robot path. And with our end result, we end up with this very, very nice map here, which we even can overlay on top of Google Maps in order to see how it maps across these 4 buildings that the robot drove through. Alternatives, well, one thing is make sure your robot has really good sensors. If it can't get disoriented in the first place, then you don't have as many problems. But barring that, another good approach is to build local submaps. Since these are larger areas, they're less likely to suffer from perceptual aliasing as opposed to just a single position where the robot is only thinking about what it immediately sees. Another approach is topological mapping, where we consider things like corners and doorways and specifically map with those. These features tend to be also less likely to suffer from perceptual aliasing-like problems. So one thing that we're going to do with our masking here is we're going to make sparser maps. And sparser maps can be very useful. What we're showing here is an example of a non-sparse map. This is dense. At every little delta of distance the robot has driven, we have another little green dot where the robot has remembered exactly what it saw in that position. And it's just putting them all along here. But as it turns out, for a lot of robotics problems, this level of detail is not actually helpful to the robot in terms of later use. And actually, if we had less detail, that would mean the robot would have less opportunity to make mistakes with recognizing where it is and where it's going. So what if we had a map that looked a little bit more like this? What if we only kept points at the interesting spots, by the corners, by the intersections, where things are really changing? Well, this will have less detail, so it's less work for our robot to remember things, and again, less opportunity for mistake. Now we do this using a mask. So a mask is just some general function, and its purpose is to tell us, is a location interesting? Is it distinctive? Or, on the other hand, is it generic looking, and we should ignore it? So whatever mask we use, we generally want it to say things like, well, that hallway on the left, that's not interesting. Ignore that. That intersection on the right, let's keep that. That's interesting. That's a good point for localization. The first mask we do is Isovist Eccentricity. Isovist is a fancy word that just means the shape that the robot sees everything in. And so here, those 2 situations, we've just closed them off to make them full shapes. That's an isovist. And eccentricity is a geometric measure of how much something looks like a circle versus how much it looks like a line. And so this is often used to describe ellipses. What is their eccentricity? How much circle it is or line-like it is. And so if something is very much more line-like, it looks more like a hallway, we say it's not interesting. If it is more circle-like, we say, there is more interest here. And that is what this mask does. The other choice one we have is an openings mask. It looks for how many different choices that you ever have at some point. In a hallway, generally, you can go forwards or backwards. Only 2 choices. At a more interesting intersection, maybe you have 3 or 4 choices. And those additional choices mean this location is more interesting, something we should remember. And then finally, for comparison, we still keep around this so-called always mask that simply says everything is interesting, keep everything, and do your best with it. The first result that we find is that using these masking functions gives us a more efficient system. If we look at the always mask over this sample path of 2.5 kilometers, 5,300 times about, it tried to recognize its location as matching something previously. 72% of the time, it believes it did in fact find a match. And computation was, it spent about 200 seconds doing all this computation and matching. When we use the eccentricity mask, it only tried about 1,000 times, because many of the locations it was in didn't try to recognize it. It said it already wasn't distinct enough. And also interesting, it only believes those half the time, so even less. And again, this comes from the fact that the locations it's trying to match are inherently more distinctive. And so it's easier to tell when they really just aren't the same place. And because it's trying so many fewer cases, it only took 50 seconds to do this computation. The openings mask also performed relatively similarly. The second result we found was that we could use rougher matches. Now, there's a couple of things I want to point out on this figure here. So the y-axis is error, and this is error in the overall map. So we're evaluating entire runs of this mapping algorithm in order to see how it performs with the final map that it evaluated in its accuracy. So x is total error in meters. On the y's, x is a matching score threshold. Again, this is a threshold that is for the entire algorithm, and it says, well, if I have this view of the robot and I have this view of the robot, how much do they have to really overlap? How much do they really have to match for me to say I recognize a place, right? Maybe as low as 30%, or maybe as high as 60%. What counts as actually making a match? And so we can vary this parameter to see what happens. Interestingly enough, with the always mask, when we give it a lower threshold, we get very, very high error. So what is happening here? Well, this is where it's saying this hallway is the same as that hallway, continually. And it's making a map that is very distorted and very off. Alternatively, down here, we get very, very low error with the eccentricity and openings masks. Because they're so much more distinctive, even only 35% overlap is actually very confident that the places are the same. And so it performs very well. And finally, through this masked mapping system, we get effective loop closures that are true, and we transform the map on the top to the map on the bottom by properly recognizing locations as the robot is going along. Chapter 3, Monte Carlo policy tree decision making. Here again, we are on the planning problem. How do you choose an effective action in order to accomplish a goal that you have? The problem we're looking at specifically in this chapter is for self-driving cars. How do you plan effectively with a self-driving car? There's a lot of difficulty to this. One is that your steering and your acceleration are all continuous action spaces, right? When you're steering the wheel, there's an infinity of in-betweens that you could be using, and the same with your accelerator. Not just for yourself, but all the other vehicles on the road too have the same flexibility. How do you plan when you could do almost anything, and so could all the other vehicles? How do you consider what they're doing when they can do anything? You also have to plan fast enough. The road is a very dynamic, dangerous place, so you need to be able to react. Your planning needs to be efficient, time-wise. And you need to plan far enough into the future that you're not making naive, short-sighted decisions. The contributions in this chapter include a framework where we combine two things, multi-policy decision-making and Monte Carlo tree search. We then give some improvements on these, including marginal action cost estimation and particle repetition. We validate on both an abstract task and a self-driving task. And we supply the open source code that can reproduce all of these results. Results end up like so. We are in the bottom left corner, and the bottom left corner is the best place to be here, because the x-axis is computation time. Less time spent is better. Also cost on the y-axis, lower cost means more efficient driving, that is getting more towards the goal, and also safer driving. Generally speaking, maintaining more distance between other vehicles. And so for any amount of computation time, our method is giving us a better result than the alternatives here. There's many other ways to do planning when you're planning with uncertainty. The simplest thing is to discretize. So drive straight, turn the wheel this much, turn the wheel this much. And then either check or eliminate every possibility. This really only works though for very small or simple problems. But it has advantage for those problems of being able to find an optimal solution. there's other ways of simplifying too. There's something called macro actions. This has some similarity, although differences, with multi-policy decision-making. There's also reinforcement learning and neural network approaches. These have been very successful, for example, with games like chess and Go. So the first thing that we're incorporating is multi-policy decision-making. The idea here is we radically simplify all vehicle choices by using closed-loop policies. Stay in your current lane, lane change to the left or to the right, or maybe accelerate or decelerate while doing one of these two. Both our vehicle and all the other vehicles on the road are only allowed to follow one of these set choices. And so that means the total number of possibilities is radically reduced. The other thing we use is Monte Carlo tree search. So here we're displaying a tree, and this is basically a picture of what plans we could make. The very top of that tree, that single dot there, that is now. That is what where the robot is now and what it's thinking about doing later. In this example, we're planning with 4 different policies, meaning there's 4 different things that we could be choosing. We're planning 8 seconds total into the future, 2 seconds at a time. So each layer here is 2 seconds after the previous layer. And with 4 different decisions to make every 2 seconds, at the bottom here, there are 256 different possible plans we could be taking. But that's just for our vehicle. We still have to consider all the other vehicles on the road. So for any one of these plans, we still have many more scenarios we need to evaluate to really know that for any reasonable thing the other vehicles are doing, we're still going to be safe and effective. So Monte Carlo tree search tries to only evaluate the most interesting parts of this in order to effectively use resources to evaluate the plans that are most likely to be the best ones. Monte Carlo tree search is able to be a little bit reactive. If it notices as it's planning that starting with a lane change left seems like a bad thing, well, it won't explore there quite as much, unless everything else seems even worse. At the end, only the best plans get thoroughly evaluated and vetted against many scenarios. The first improvement then, after just combining these 2 prior methods that we make, is something called marginal action costs. So in classic Monte Carlo tree search, for games like Go and chess, all you care about is the final outcome. All that really counts is, did you win, did you lose, or did you tie? Nothing else really matters. But that's not exactly the same with our self-driving car scenario. For one, if we're planning 8 seconds into the future, we're not actually getting to Miami right away from Michigan. And so we have to consider the structure as being fundamentally different. Really, the question is, over every 2-second interval, what happens there that matters? In those 2 seconds, did we make progress? In those 2 seconds, were we always safe? Were we always maintaining as much distance as we could between the other vehicles and us? And so, mathematically, the formulation of a node cost in classic Monte Carlo tree search is we simply take the mean of all terminal costs, of all final outcomes. Whereas what we're proposing is much more effective for this form of problem structure, is where we have the expected cost of a node being the marginal cost of that node estimated on its own. So that is just the things that happen in this 2-second interval prior to that node, plus the minimum, that is the best choice from among the child actions, the things that could happen next. And for this structure of this self-driving car scenario, this ends up being much, much more effective and efficient. The next improvement we make is called particle repetition. So here what we're considering is, okay, there are lots of different scenarios to consider. So as we plan any path through the tree, any of these different decisions we could make every 2 seconds, we start by taking a random sample of what all the other vehicles might do to compare against. And as it happens in this scenario with self-driving, most of these things are benign. Most of them are kind of boring. But there is some small number that can actually be quite dangerous. And so, in order to reduce the variance between our different estimates the most, we actually repeat scenarios on a worst outcome first basis, because it's those worst outcomes that are most likely to be high variance in the first place. And so by testing those ones more selectively as our main comparison between all the different plans, we're more effectively able to determine which plan is actually best. Dangerous things tend to be closer calls and tend to have higher variance, and so they benefit most from this repetition. And again, our results here are quite good. We end up with both more efficient, safer driving, as well as getting this with less computation time. I now want to talk a little bit about work in the appendix, learned similarity Monte Carlo planning. This work was not quite as successful as the prior work, but still has a lot of interesting points to it. So in the last chapter, we combined multi-policy decision-making and Monte Carlo tree search. They served different functions there. Multi-policy decision-making was fundamentally about taking advantage of certain problem structure. Just the fact that we could effectively factor things into several different policies is not something you can do in any planning problem, but it does work very well for the driving-like scenario. So multi-policy decision-making allows us to take advantage of that structure. Monte Carlo tree search is much, much more general. It can be used from anything from playing a Dota video game-like things to chess, or really this self-driving car scenario. But in turn for being so much more general, it really doesn't inherently take advantage of structure in the same way. And so in the previous chapter, by combining them, we got both of those advantages. Now, ideally, what we would have is some general structure, kind of like Monte Carlo tree search, that could take advantage of specifics from a problem when they are available. And so one thing we noticed also in chapter 3 was that there was significant redundancy sometimes, where certain actions would generally have the same results because of certain things about their circumstance. Well, what if we could try to find some way to automatically remove this redundancy, but in a general way to get more efficient planning? In a general way where we could do this for any POM-DP, where POM-DP is a general mathematical framework for problems in planning that have uncertainty. So the contributions that we have here are a method to avoid redundant calculations by taking advantage of similarity. That is, combining results for states and actions when those states and actions are similar to each other. And also learning that similarity with a multi-layer perceptron and Euclidean mapping. At the end of the day, this is in the appendix because the results were not the best. We had some advantages over our baseline method, which is POM-CPOW, or partially observable Monte Carlo planning with observation widening. But another one of our baseline methods that was trying to emulate DPQ learning did even better. So additional work would be necessary here to understand everything. Alternative methods, though, for this kind of taking advantage of planning problems and structure. One is called continuous rapid action value estimation. It works in a similar way because it tries to share information between states and actions when they're similar in some way. There's also Voronoi progressive widening, which takes a different approach. It tries to intelligently choose what actions in the continuous space to explore most effectively. And Bayesian optimized Monte Carlo planning, which has a similar goal of choosing actions intelligently, but takes a different process to do this. So we're trying to learn similarity. And we try to do this by having a multi-layer perceptron, a simple neural network that we learn that maps state-action pairs into a Euclidean space. So when these are mapped together in the space, and they end up very close together, that indicates that they have, say, a similarity that is high, like close to 1. If the network maps these state-action pairs, and they end up very far away from each other, then they'll have a similarity of 0, and they won't be sharing information between each other. So mathematically, we do that like this. Now, in order to learn this, we have to set up a loss function. And so the first component that we chose was regret. Where regret is the difference between the best action that we should have taken and what action we thought was best but were mistaken about. And so if we do in fact indicate the right action, we have no regret, a regret of 0. And the bigger the disparity between how good of an action we think was best and the actual truth, the higher our regret, because we made a worse decision for that scenario. The next components include trying to get the correct value, that is, through similarity, we are estimating the right value that we would have gotten if we didn't use similarity at all, but we used a lot of computation power. Also advantage, that is the relative value. How much better was one action than another, even if we don't absolutely know what their values were. And also bias. We want bias to be as close to 0 as possible. That is, we overestimate just as often as we underestimate. And putting all this together, at the end of the day, again, our results were not always the best. But let's point out a couple features here. So in the first column, we have the number of trials. This is the number of different random scenarios we sampled in the beginning that came down through some different path through the tree that we were able to examine. Then the first column is POMC-POW. That is our baseline method, and in fact, our learned similarity is in fact built on top of that. The middle column is what we're labeling as a value network. So this is POMC-POW, but augmented with a value network. The network is the exact same size as we're using for learning similarity, but it just directly tries to estimate values instead of trying to do the mapping into a Euclidean space for then calculating similarity. And then finally, we have our own method. So in this first problem here, apparently the problem was structured in such a way that our learned similarity method does do significantly better than the baseline POMC-POW for the same number of tries. However, the value network seems to do even better. So there's some aspect here in which these extra steps of walking from state actions into similarity, into a Euclidean space, into similarity, and then back to values, was apparently losing some amount of information then could be directly achieved with the value network by itself. And then in the second, much more difficult problem, we actually find that our method is doing much, much worse. And we suppose that there must be some essence here in which we're not properly limiting the bias. There are some steps we've taken to try to limit bias, but the performance is so much worse, and that's likely because it's actually hurting by biasing things improperly. So in conclusion, throughout this presentation, first we determined robot and radio locations in a cluttered lab by smoothing but not simplifying the raw data. We then mapped a 2.5 kilometer path, principally by choosing to only remember the most distinctive locations. Then we planned fast, safe, and effective driving by using marginal action costs and particle repetition. And finally, we explored another approach for faster general planning by sharing information between similar states and actions. Finally, I'd like to acknowledge my advisor, Ed Olson, and my committee, Ella Atkins, Dimitri Berenson, and Chad Jenkins, and also my long collaborator and former lab mate, Max Krogias. Thank you.